Shall we start control group meeting? Today I invite Mr. Akshay. Could you introduce yourself?
Hello everyone. I am Akshay Baheti. I am a PhD research scholar in IIT Delhi, PhD program with the University of Queensland. My current research topic is life cycle risk assessment of reinforced concrete structure under earthquake and fire.
Okay, thank you.
Yeah.
So he will be a candidate for Suzuki program to come to Japan after Saranya-san. Did you discuss with your family?
I discussed and I will soon start filling the application form.
Okay, good. Okay. Well, anyway, there will be controversy, so I cannot promise, but yeah, I believe possibility is very high. Okay, so and also today I asked Ahmed-san to make a presentation about his master thesis. Ahmed-san, are you ready?
Yes, I do. That's Sensei, I'm ready.
Okay. Originally from Egypt. Oh, maybe you should introduce yourself also.
Okay, I'm originally from Egypt.
Mm.
I moved to Japan as a part of twinning program between USM in Malaysia and TUT in Japan to get a kind of double degree, another master program here in Japan.
Okay. So if you are ready to start your presentation.
Yes, sure.
Oh, it's a Tom Cruise.
Ah.
Right? It's a movie, right?
Yeah, I like this movie.
Yeah.
This yeah, so is it clear to anyone, my slide?
Yeah.
So I prepared this presentation for the control group today. So let's start with my title. My title was Evaluation of the Seismic Assessment for Regular RC Buildings with various retrofitting techniques based on fragility curves. The is me, Ahmed Rojdi, and my past supervisor was Prof. Fazli in USM. Let's start with the introduction. First, the introduction is important to show what earthquake can do things, especially the irregular buildings and mid-rise buildings. Many buildings are prone to seismic damage because of the irregularity or the irregularity on the load distribution or the irregularity of the mass or the stiffness. So the most common of buildings for mid-rise buildings, especially because it's prone to neglecting seismic design. Most of the designers not in all countries, they neglect the seismic design, especially for mid-rise buildings or short-rise buildings. So that's why it's severe a lot during earthquakes. So we need to consider or we need to pay more attention for mid-rise and short-rise buildings, especially irregular ones. This another part of the introduction. I wanted to talk about the retrofitting techniques, which can be used to unsafe buildings or the buildings which find due to or according to seismic codes So I presented here 4 types of retrofit. First type is the RC jacketing, which is the most common technique in our countries, especially in the second one is the steel jacketing. Actually, they have the same concept, which is about increasing the stiffness of the elements itself. Third technique is to add steel pressing to the building, which is about increasing the stiffness of each structure member. It's about increasing the overall stiffness of the building and the overall seismic performance of the building. Last one is the base isolation systems, which can enhance the seismic performance and isolate the building during earthquakes. Third part of my introduction is to show what we are going to do. First, I wanted to show the various damage state which can each building suffer during or after earthquake. We have five damage state can happen after each earthquake. The operational, which means the building is still safe and still operating. The immediate occupancy, as we can see, we have small damage in our building related to the non-structural elements. Third damage state is to life safety, which we can see there are cracks start to appear in the building. Last one is collapse prevention. Our building is already collapsed or already unsafe after the earthquake. Last thing in our introduction, I want to show what fragility curves mean. It's a graphical representation of the probability of failure or damage of structure due to seismic events. If we have a structure and it's under earthquake event or special seismic event, it may suffer or it may show some performance after the earthquake. We need to show the probability of failure or probability of damage for our building under different damage states: pressure, immediate occupancy, life safety, or collapse prevention. This is the purpose of using the fragility curves of fragility assessment. The objectives for my research was divided to 2 main objectives. The first one is to evaluate the seismic performance of buildings with different retrofitting techniques. Sure, we will use the nonlinear dynamic analysis. I use the nonlinear dynamic analysis to show the lateral displacement of the building before and after adding the retrofitting techniques, the maximum story drift, the story shapes, and the mode shapes and time period for each model before and after adding retrofitting techniques. Second main objective is to develop the vulnerability assessment, the fragility assessment, and it was divided in 2 steps. First steps is to develop the incremental dynamic curves and get the data from these curves to do the fragility assessment. So the objective of my research, first, to study the seismic performance in these terms. Second is to develop the fragility assessment. Then I did a small literature review that shows how the previous research talked about this point. All of this research showed that there is a significant improvement in the seismic performance of the buildings after adding different retrofitting techniques. We can see in the first one, after adding the pressing, expressing. The second one discussed the performance after adding the steel, and third one after adding the RC jacketing to the buildings. All of them, they can show a significant improvement. As second one, after adding steel jacketing, it shows a drift decrease in both directions by 40 2% and 32% in X and Y direction, and the ductility improvement in both directions too. And the third one also, after acting, it shows the drift ratios reduced to this ratio 0.08%, and also that the capacity, the loading capacity increased by 124% and 150% in both directions. That was a small literature review. After that, I did my methodology. That was my methodology. First, we started to define the structural configuration of our buildings. We choose two types of irregularity in our buildings. First one, building with horizontal irregularity. Second one, a building with vertical irregularity. Then we determined the building vulnerability parameters. The first parameter is P1, which is about the irregularity. We'll change the irregularity. Second parameter is about the retrofitting techniques. So we have two buildings with two different types of irregularity, and we will apply two different types of retrofitting techniques on our buildings. Then after that, we did a linear analysis, just a response spectrum analysis, to set the target response spectrum. Second, to design the building after adding the retrofitting techniques. After making sure that the building is safe, we started to seismic events, our seismic scenarios, from here. Here is a big database, internet, which we can use, which we can download many seismic events from it on the internet. So we used many seismic from here and started to do our nonlinear dynamic analysis after making sure that all elements are safe, to show the effect retrofitting techniques on our building. So we did the nonlinear analysis. We determined the damage state. We have 5 damage states, and we after performing the nonlinear analysis, we developed the incremental curves, the IDA curves, and then we took some data from these IDA curves and put it in the probability equation, the fragility assessment. So first, we choose the two types of buildings. This is the buildings data was with vertical irregularity, and building 2 with horizontal irregularity. Both of them, they were residential buildings. The story heights are shown in the table. The concrete grade is 30. Repair yield stress is 400. We have the beam size around the parameter of the building. The importance factor is 1. We have the behavior factor for the first one is 3.2. And for the second one is 4 behavior factor, which we used in the code. This because the Euro code mentioned that buildings with vertical irregularity reduced by 20%. I'm talking about the behavior factor. And the viscous damping is 5%. Base support is fixed. And the second table shows the vertical loads on our buildings, the dead and live loads, which we used. And last table shows the column section. We used the corner columns, edge interior with the reinforcement, and the beam sections with reinforcement for building 1 and building 2.
Ahmed-san, could you explain what kind of irregularity building 1?
First building was with vertical irregularity. We can see in first 2 stories and first 2 levels, there is a big the middle of the slab. Then after that, there is no opening anymore.
Okay.
This for building 1. Building 2, as we can see, the plan is not irregular, is irregular. we can see is as T-shape. T-shape, yeah. So first one is with vertical irregularity, and second one is with horizontal irregularity.
Okay. Okay.
Okay. Of buildings, they were unsafe at the beginning, so we applied two retrofitting techniques for each building. First one was RC jacketing. Second one is steel pressing. This is just a proposal for the retrofitting techniques that we use. For jacketing, we will apply the jacketing only for the unsafe members, the unsafe columns or unsafe beams. And for the steel pressing, apply the bracing, X-bracing, until the other structure members become safe.
Oh, but you said the building one doesn't have a column in the middle, but it looks there's a column.
No, this is just a proposal. This is just a proposal for the retrofitting technique. Yeah.
Okay, so it's not the building one. It is.
Yeah. It's not building one or two, just proposal for the
Okay.
retrofitting technique that we used.
Mm.
After that, after choosing the
Mhm.
after choosing the buildings, the regularity, after choosing the retrofitting techniques that we for each one,
Mhm.
we choose the we choose the seismic events that we will use the nonlinear analysis.
Mhm.
Which for me, I started with 3, but later I got enough time to continue up to 4. I chose 7 seismic events from different places, but the lowest magnitude is 0.6, 6.5. I tried not to go lower than this magnitude, and of course with different source locations, as you can see, RGB, different source location, and with different usable frequencies. So I tried to choose different seismic events with different properties. And I applied each seismic events in both directions, X direction and Y direction. Each seismic event on peer database, it has let's say that it two seismogram in both direction, in X and Y. So this kind of 2D nonlinear analysis. I mean that I applied everything in both directions. The nonlinear analysis was on a 3 model in both directions. So according to the Eurocode, to consider the nonlinear analysis in X direction, I have to add 30% of the seismic event Y direction during the analysis. I did the same for the Y direction. I added 30% of the seismic force in X direction to the main force of Y direction.
But each earthquake has 3 components. Why?
It has another vertical component, but my study was only related to the horizontal force.
Yeah. But horizontal force, you have 2 components.
I got 2 components for each earthquake, horizontal one and horizontal two.
Yeah.
Two seismograph. On peer, it also has a vertical component, but for me, I had a vertical analysis to the buildings.
What is the meaning to add to 0.3 of opposite?
Actually, this was a code. It's kind of it means that the seismic force is not 100% in X direction, 100% in Y direction. It may be in angle between them. So we need to consider, if we need to study the X direction, we need to consider 30% of the force in Y direction. Or if we want to study the Y direction, we need to consider 30% of the force in X direction.
In case of design earthquake, you have a real record with 3 components. uh, okay.
Also, it's not only for the design. According to the Eurocode, it's also we can use that in the nonlinear analysis.
Mm. Okay. Yeah, please continue.
Okay.
Mm.
So after the seismic events, we had to match it with the target response spectrum for our buildings.
Mhm.
So as we know, the matching it depends on the target response spectrum of the area of analysis. So I did matchings for our buildings. This building one, as we can see, the gray the actual elastic spectrum,
Mm.
and the black curve is the target spectrum, and the red one is the after scaling image spectrum of the seismic events, but after scaling for building one in both directions, and building two. So I did that in both directions.
あ
Uh,
待てよ。the gray, the
the
gray
gray
one,
is the response spectrum for the 7 seismic events.
yeah, and you scale
Yeah.
earthquakes to match
Yes.
to the target spectrum.
Yes.
So you also, I don't know how to control, I mean, amplitude. You also, I don't know. うーん、
It was a kind of amplitude matching, something like that.
but the shape of spectrum is completely different from target spectrum and real spectrum. How you
Yes,
can,
yes.
how you can scale?
Uh, Using softwares like ETABS or like Seismograph.
Mm, mm.
And the
Sometimes
scale
we
you,
generate artificial earthquakes based on target spectrum, and also adapt phase information from real earthquake. This is a technique I know, and I have used
mm,
this technique.
mm.
Is it the same in your
Maybe it's the same. Yeah.
view? Okay. Anyway, please continue.
Okay, so after choosing our buildings,
Mm.
after choosing the retrofitting techniques, after choosing the seismic events and matching it with the target spectrum, which we will use in the nonlinear analysis, we started our analysis. First, we do the linear, the response spectrum analysis. This is the Eurocode combinations for the seismic design to just to make sure that after obtaining techniques, the structural elements are safe. Uh, this is the building first. This is the 3D building. The seismic force, we can see that this was a linear analysis, just response spectrum analysis. We can see the red columns in the first are the unsafe columns. You can see the design ratios are more than one. The red columns more than one means that these columns are unsafe. So this was before retrofitting. We applied the RC jacketing as a first option. Then we applied a steel bracing as a second option. As we can see, after applying the retrofitting techniques, the building becomes safe. So first step is to make sure that the buildings are safe under retrofitting techniques. Of course, I did that for both buildings, for building one and building two, but for it, I just showing you the building one only. So after making sure that all structural elements are safe, I started to do the nonlinear analysis. The nonlinear analysis started with or with developing the incremental dynamic analysis. So first table shows the parameters of incremental dynamic analysis. Number of intensities is 20. The intensity label is the peak ground acceleration. The demand drift, we choose the drift as a demand parameter, and the total performance level is 5. As we can see in the second table, 2008, we followed this research, Chui 2008. We choose 5 rating, the damage control, life safety and collapse prevention, and IO. The maximum drift for state is mentioned here in this table, 0.5, 1, 1.5, 2, 2.5%. So after applying the incremental on the buildings, as we can see in this Excel, we started to increase our ground motion intensity from 0 to 2G, and we start to record the drift ratios for each ground motion intensity for all without retrofitting and with bracing and with jacketing for both buildings. We did that for both buildings. So after developing the incremental analysis, we get this data and apply this data to the probability equation, to get the probability of each damage state to happen for each building. This we call this the fragility assessment, and this is a small flow chart that shows all the fragility curves. We get the data from the incremental dynamic analysis as a first step, and then we apply these data to the probability equation in an Excel sheet. Then we get the probability of each damage state to happen under different motion intensities. So this was the last step of our methodology. So this is the important part about the results. First part of our results is about the objective one, which shows the lateral displacement. As we can see, the first two curves show the displacement in X and Y direction. For the red curve is the curve without retrofitting, the building without retrofitting. The blue one with RC jacketing. The third one is the building with X steel bracing. We can see that there is a significant improvement after adding the bracing. After adding this RC jacketing. Of course, the building is safe in both methods, but in both retrofitting techniques. But bracing shows more significant improvement. We can see. Sorry. So this is for the first one, and for building 2, it was almost the same improvement. The building 1 was the one with irregularity, and building 2 was the one with horizontal irregularity. We can see a significant improvement on the performance related to the lateral displacement. See as an example for building 2, the displacement reduced by 87% and 71 Y directions respectively. Also, it happened for RC jacketing. It's only reduced by 54% and 50 X and Y directions respectively, of course. So, of course, we can say that the X steel bracing is more effective than the RC jacket, according to the lateral displacement data. And this the inter-story drift. We can see a significant improvement after adding the bracing. The green curve and the blue curve shows the RC jacketing model, and the red curve shows the without anything, without retrofitting. This for building 1 and also for building 2. You can see the bracing reduced that drift by 79%, in X direction, while the RC jacketing reduced the story drift by 48% in building 2. I'm talking about building 2. This in X direction. So we can see the lateral placement becomes lower after adding X steel bracing. This means that the lateral or the shear force will be higher. We can see the story shear force is higher in the case of bracing than the case of RC jacketing than the building without anything, without most retrofitting. We can see for building 2, as an example, the maximum shear force is increased after adding the X bracing by 85%, while after adding the RC jacketing, it's only increased by 17% in X direction, and according to the story shear force. The last point in the first objective, the mode number, shape, and the time period, and for each mode number, as we can see, the time period for the building without retrofitting is higher than the building with jacketing, is more higher than the building with RC bracing. This building 1 and the same happened. We can say that the time period is reduced after adding bracing by around 32%, and the RC jack, sorry, 52%, and after adding RC jacketing, it's reduced by 29%. Also, of course, this happened for both buildings. But the most important thing that the first 3 mode shapes for all models were the same. We can say that the first mode shape was the dominant translation was the X translation. The second mode shaped one with Y translation, and the third one was torsional translation. We know that if the first mode shape is torsional, this means the irregularity is very high, and our building is not good with the irregularity factor. So the good point for all models that the torsional shape it became on the third one, on the third mode, which is a good point. First point in the objective number 2 is to perform the incremental dynamic analysis curve. You can see this relation is between the ground intensity 0.2 G, 0.5 G, 0.8 G, up to 2 G, and the corresponding IDR, which means the inter-story drift for each building. And this table shows or summarizes the data from these graphs. We can say, as an example, to reach collapse prevention, or let's say the operating state, to reach the operating state for the building without retrofitting, we need intensity of 0.13 G. The same building, but after adding bracing, this intensity becomes higher G, and after adding RC jacketing, it becomes a little bit higher, 0.2 G. We can say we can see it in the performance after adding bracing and after adding RC jacketing, but of course, after adding bracing is more effective. The building number 2, building 1 and 2, same effect.
Why this line is straight? Is it analysis, non-linear?
For my analysis, it becomes linear. It was a linear, yeah. The IDA was a linear analysis. So
Linear analysis?
no, I don't mean the linear. It's analysis, but the result becomes, as we can see, like that.
Why? If you use the intensity of earthquake vertical axis, you will get more drift, right? So the curve will be going gradually. Why it is going straight?
Uh, I don't no, I don't know that, but I know some IDA curves show some nonlinear or the sometimes the IDA analysis shows some distortions in some points,
Mm.
but this didn't happen with me.
So horizontal axis is IDR is
The interstory drift,
story. You have
yeah, the
many stories.
interstory drift, yeah. And the
Interstory drift of
yes, and the
maximum
vertical
one.
one, sorry,
First story or second story? Which story?
this is the maximum one
Maximum.
for the build, yeah, in both directions. In X, the maximum of X, and in all stories.
And why there is only one line?
No, we have three lines.
Yeah,
The
but
first, the green one
one
with
building,
tracing.
one line, right?
No. One building, one curve, one plot. The plot on the left side is for building one, and the plot on the right side is for building two.
Mm-hmm.
The green line
Mm-hmm.
with bracing and with
Yeah,
jacketing,
I
and
know,
the
I
red
know.
line without
Yeah,
without retrofitting. Yeah.
For example, red line is without retrofitting,
Yes.
and you get this line by one earthquake,
No, by
gradually
seven.
increasing the intensity.
Yeah, but by seven.
Seven
This
earthquake.
this is the average line of the seven earthquake
Average
events.
line.
This is
Okay.
the average line. Yeah, I did the same for each seismic event. We have the same plot, but this is the average one.
Okay. Mm-hmm.
Uh, so this was for the IDA analysis. We can see that the slope of the line without retrofitting, and it became higher after adding retrofitting, especially after adding the bracing. This means that to uh, to reach this interstory drift using bracing, we need a higher ground motion intensity, which is considered a good, as an example to reach the 1.5 interstory drift, 1.5 per story drift for building one. We need around 1.25 G
Mm.
with bracing, while to reach this with RC jacket, we only need around 0.6 G. And to reach this story drift ratio without retrofitting, we need we can say 0.4 G.
Mm-hmm.
So which shows a good improvement in the performance after adding, also after adding the RC jacketing, but is not as high as the effect as adding steep bracing. Last point in the second objective. This is the fragility assessment. This is the fragility curves for the first plot is the relation between the probability of reaching each damaged state, and the horizon is the big ground acceleration intensity. First plot shows the effect of bracing relative to the original build. Second plot shows the effect of jacketing relative to the original building. We can see the probability of the damage state become lower after adding the bracing. We can see the red operating state, the green curves, the life safety, the purple one is collapse prevention. Means that each curve shows different damage states. Means that, and the line is after applying the retrofitting techniques. The solid line is the building without any retrofitting techniques. So that we can see the probable damage or of reaching the damage state becomes lower after applying the pressing for the first plot. And in the second, we can see the same. After adding the jacketing, the probability of reaching the damage state becomes lower, but not as the same effect as. And these tables also summarize the data from these plots. As an example, in intensity measure of 1G, we can say that for building one, to reach the collapse state, the probability of reaching collapse prevention state is 4% without retrofitting. The same, the probability of reaching the same damage state after adding pressing, it becomes 0.29%. And after the RC jacketing, it became 1.2%. You can see a good improvement of the P of reaching each damage state. Of course, after adding different retrofitting techniques. Also, the same happened for building two. We can say that the same happened for the building two. The probabilities reduced after adding the retrofitting techniques, which is a good thing. And we can see that in these plots and these tables. Any questions related to the fragility curves?
Mhm. Oh, Akshay-san gave a comment.
Huh?
Did you receive?
Yeah.
Mhm. Mr. Akshay, you can speak.
Okay.
Yeah, sure.
Um, um, first of all, I would say very nice presentation. It was very clear to understand everything.
Thank you.
However, I struggled at a point when you showed the fragility results of the fragility analysis. Therein, it was concluded that the building with bracing is more efficiency than building with RC jacketing.
Yes.
And when you were discussing the results from the nonlinear dynamic analysis, therein I think it was concluded that the building with RC jacketing was more efficient than the building with bracing. So these results are like um, opposite to each other.
But which point specifically in the analysis? The lateral displacement
Uh,
or the drift?
Drift, I'm talking about drift only because for fragility also you have used interstory drift
Yes,
means
the demand parameter.
phenomenon, right? Controlling phenomenon. Yeah. So for interstory drift, it was observed the building with RC jacketing was showing a very less drift
Yes,
than the
yes.
bracing. If you can go back to the
Yeah,
non-linear analysis.
sure. This is the drift? Yeah.
Yes. No, okay,
Yeah.
that I mistook.
Mhm.
It's okay, means yeah, this I confused with the green and blue line.
No,
Where
yeah, green line is the bracing, the blue is the
yes,
jacketing with jacketing, yeah.
yes,
In all cases, let's say that in all cases, the RC, the steel pressing shows as the higher improvement, the highest improvement in all cases in the displacement and the fragility results in the incremental dynamic results. We can say that the steel pressing it showed that the highest improvement But there is another point I will talk about it in the conclusion. I can say that the pressing is more effective than RC jacketing, but we didn't. This point of research is only about the structural performance. The research didn't include anything related to the economical issues or the construction issues. Know that we're adding steel pressing is more. I think it will be more expensive than adding RC jacketing. We can say it can cause a higher improvement or a good improvement relative to the RC jacketing, but we need to consider the economical issues of that. Of course, it will cost a lot of money. Also, how much it's easy to construct the steel pressing in the building relative to the RC jacketing. Maybe it's not that easy. Maybe there is some architectural issues to add the steel pressing in the building. So this research is only considering the structural performance for all buildings, but it did any economical issues, any construction, any architectural issues. So that was a kind of recommendation for further researchers. Yeah.
Okay.
Thank you.
Well, anyway, you did research only within 1 year. Is that correct?
Around 6 to 7 months. Yeah.
Around 7 months.
Yeah.
Okay. So, yeah, very good. And how did you do amount of retrofitting? When you for example, jacketing, how did you decide size
Uh,
of jacketing? And
it depends on the number of unsafe elements. I just applied the jacketing for the unsafe members, and the thickness of the jacketing, or the thickness of the applied members depends on the seismic design, the linear response spectrum design. I didn't apply it to the whole building. I only applied it to the unsafe members.
But what is the target of retrofitting?
The target retrofitting is to make our building safe in the response spectrum design. Yeah,
Wow.
this is the first target to show to show how much is the improvement that can be achieved after applying the retrofitting.
Yeah, usually you must do some iteration.
Yeah. I would do that, but that time sessions it was only 6 or 7 months, so I couldn't do many trials or many iterations. Yeah.
Okay. Anyway, thank you very much. Yeah.
You are welcome, Sensei.
Well, this group is control group. Control groups. We discuss retrofitting not conventional way, maybe using some response control device or seismic. So, but you can apply those, new device to the building, and maybe you can do the same thing, implement the dynamic analysis and the predictive valve also. Okay, good. Okay, so thank you very much, Ahmed-san.
You are welcome, Sensei. Thank you.
And
thank you, guys. Thank you.
Zafira-san, could you close your window, Ahmed-san? I just want to, Ahmed-san, because you are now, how to say, second year of master course, And I just want to explain how to apply doctoral course. I mean, scholarship. can you see the website? Grace program.
Yes, it's clear.
Okay. So, for example, first you go to university website, doctoral program, and if you click architecture and civil engineering, no, I made a mistake. No. Admission. Admission and Japanese government scholarship. Okay.
Okay.
And you can get this one, Japanese government scholarship. Well, it is this year. I mean, you will apply next year. So this information updated, old one. Yeah, but it will be almost the same. And let's see. You go down. You can see the schedule. Application will be. Oh, it's very close. It's very close.
The deadline?
ちょっと待って。アプリケーションがあるんで、アカデミックエントリー、イグナッツの点でやるように。違うな。ちょっと待って。OK。アッパーワン。Yeah, アッパー。そうだね。Special program. Yeah, special program. This is only architecture and civil field. So, and only from Asian and African countries. So you are from Egypt. So I think you are eligible to apply for this.
Yes.
And let's see. And we can accept 8 doctoral course students. So this number is very high. So it's a big. 8 is we can accept 8, but scholarship is only 4. But still, this number is very high. And I think you are eligible. Application procedure. Complete the application January next year.
Oh, okay, good.
So please remember this one.
Okay.
And Zafira, you also, I mean, apply the same program, right?
Yes.
Yeah. So Ahmed-san, if you question, please ask Zafira-san. She knows.
Sure, yeah.
Yeah. Okay. Okay. And then Zafira-san.
Hi.
I have a question about last time you didn't lab meeting.
Sorry, Sensei.
So at that lab meeting, we discussed first about the conference, JES.
Yes.
And I'm waiting for invoice and receipt.
Okay, I will give today, Sensei.
Yeah, I Hajima Sharafi and Ataya-san already. So only I'm waiting your receipt and invoice. Okay. Another thing is we plan to go Sumitomo Riko company. They develop this viscoelastic damper, and this is so Friday next week, and we meet 9:30 my room and go by Komaki City by car. Okay, you will attend, right?
Yes, Sensei.
Okay. That's all. So, Zafira-san, do you have anything you?
Yes, I do have, Sensei. I will share my screen. Can you see my screen, Sensei? So as we discussed last Monday, so I create a flow chart. Can you see my screen, Sensei?
Yeah, yeah.
Okay. So first of all, we start with the coupling wall with steel beam, and then we run check with capacity spectrum. And then we have a few design criteria that we want to look at. First of all, a story drift, and then wall ductility and beam ductility, and also degree of coupling. So the model pass, we doesn't need to apply damper. So, but if not, but we try to apply a damper, metallic and viscoelastic, and also hybrid damper. And after we apply, we'll use displacement-based design method to get the successful design. Sensei, do I have to explain to Ahmad about the system or later? Maybe later. We don't have much time today.
Maybe later.
Okay. So we start with the two steel beam, two different. One is 600 times 250, and another one is 750 times 350. So this is the interstory drift by capacity design spectrum. As we can see, the blue line is for 7.5 meter wall. For the green one is for 5 meter, and the red color is for 2.5 meter wall. And the limit that we saw 1.28 centimeter, which is 1/250 story drift. So as we can see, the story drift based on capacity design spectrum is more the limit. And after that, I check the wall ductility. As we can see at the bottom wall, every wall, especially for 7-point wall, the ductility is very big. And also ductility 2, wall number 2, is also big. It's almost 18 and 16. And here is from Serracini. So as we can see, when the wall length is become bigger, the ductility become high. So also same with the beam, steel beam with 700 times 350. The ductility of the wall increase when the wall increase. And
So could you stop?
Hi.
So actually the 7.5 meter, definitely it is stronger.
Yes, yes.
Right? And the 2.5 is weak. But the damage higher for 7.5 meter.
Yes.
Why?
In this model, Sensei, the thickness of the wall is the same throughout the so when the length of the wall increase, the width of the wall also increase. Probably because of the width increase, then it have more loading, compression loading to the wall, excessive loading to the wall. That's why it's possible to have damage on the wall.
How about the story weight?
Story weight is maintained the same.
Same way.
Yes.
Yeah. I think, for example, how much natural period of the 2.5 meter? Natural
2.5.
period. T.
I will open the so for 10 story, 2.5 meter. So this is the consent.
Natural period.
Yeah. So we can take 100%. So it's about 0.6.
6. And
Yes.
how much for 5 meter and 7?
5 meter is 0.4, and 7.5 is about 0.3.
Oh, okay. Could you go back to the slide? Okay, so okay, yeah. So if we plot curve, probably this is 2.5, and this is 5 meter, and probably this is 7 meter, 7.5. So strength is higher.
Yes.
right? And this is SA, SD. And when you draw demand curve, I mean earthquake, I cannot change the color. I don't. と、So you apply the capacity spectrum method.
Yes, sensei.
So you have a capacity curve and a demand curve.
Yes.
Could you show me what is the curve?
5 meters, okay?
Yeah.
Okay, so 6 and 750. So this is 700 times 350. Okay.
Oh, okay. So this line is a capacity curve of this building. Right. So this is which one? This is 5 meters?
This is 5 meters, sensei.
5 meters. 5 meters. And the ductility is from something less than 2. Okay, could you show me 7.5 meter same curve?
Okay.
Okay, it's much higher. And the capacity performance point is where? This point?
This one. No, performance point is the orange color and intersection with this dotted line. Yeah.
Okay. So this one.
Bit up here. So how to say? So if you draw capacity curve together, this is 7.5 meter. Yeah.
And 5 meter probably something like
Lower. And ductility line also.
2.5 is also.
Yeah.
But you assume same story drift like a yielding point, right? Yielding point is 1/250 maybe.
Yeah.
No matter of the
wall line.
width of the wall.
I should change the story drift ratio, the limit drift ratio.
Yeah. Because from this picture, it is how to say yielding probably around here.
Yes, and
the 5 meter maybe around here,
Mhm.
and 2.5 maybe around here.
Okay.
So you assume that in all cases this point is like 51. But actually, in case of 7 meter width, this is already, I mean, a lot of damage in the beam, in the wall. So ductility factor is not 1. Okay, we can discuss later
Okay.
about this. Maybe let's have a meeting face to face.
Yes, yes, yes.
Yeah. Okay.
And then after that, I also checking the coupling beam ductility. Most of the ductility of the beam is less than 5. And then I also check the degree of coupling. And I make the checking table. Should I clear the... Okay. And a box is the small beam, and the bottom one is the big beam. So we can see here the limit drift is more than 1.2. And then the ductility of the wall also for 5 meter and 7.5 doesn't fit with the criteria that we're looking for, and we doesn't with the coupling beam ductility, and also the degree of coupling only for 7.5 is too big. And then after that, to check the how much improvement that we can do with metallic damper and viscoelastic. So as we know that metallic damper only less than 30%. So I took 20% for metallic damper, and then viscoelastic is I also run placement-based design, but I only show the result here to make it simple. So the good performance is around for 5 meter wall is 40% to 80%. And then from here, we make a combination between 80% to 40% with 20% metallic damper. And see here from 80%, this is the performance curve, capacity curve and the target performance. And this is like over design, so we can reduce more viscoelastic capacities. So we get here, and then 40% is perfectly matched with the capacity. And then we check the ductility. Actually, the ductility of the wall is reducing. And I also check with the Stera 3D. After that, I check with time history analysis. So the storage to 8 centimeter. And then I make another checkbox for the performance after we put this the hybrid damper. Satisfied after we put the damper.
Okay. So, なんだろうな。So you propose a hybrid damper combining metallic and viscoelastic damper.
Yes, yes.
And why you propose hybrid damper? Only metallic or only viscoelastic? Not good?
If I can show you, for example, 10 story under 5 meter, is actually it still can sustain viscoelasticity is not that bad, but when I call the metallic, actually the performance is better than only single. For example, this is 20% viscoelastic. Can you see my screen, Sensei? So this is 20%, and this is 40%.
Viscoelastic damper.
Only viscoelastic.
Well, it looks okay.
Yeah, it looks okay. But the purpose that we put metallic to indicate excessive earthquake if like, for example, the larger earthquake come to that situation, so the metallic damper actually become like fused to the damper. So in the idea for the hybrid damper.
Yeah.
Mm.
But so if you adapt the hybrid damper, actually metallic damper in like a fuse.
Yes. That's the original idea that we
Yeah.
propose.
Did you check the hysteresis of the coupling beam? Metallic damper is yielding.
Sure. The metallic damping start to yield less than the top. So for example, this is 5th story, and this is
So this is the metallic. This is the
yes,
viscoelastic damper.
viscoelastic. Let me check the. So this is 80% viscoelastic. Okay, and then.
Oh, okay. Oh, okay. Oh, looks good. Okay. Yeah. Okay, I will explain for other people who about the meaning of this damper. So if we put only viscoelastic damper, damping force may exceed, much, and it may damage, members or connections. So we want to somehow limit upper and lower of damping force of viscoelastic. That's why this element has a metallic damper at both ends and a viscoelastic damper in the middle, and metallic damper again. Yeah, so this is a model of coupling beam. So if this viscoelastic damper exceeds, shear force, this metallic damper start to yield to limit the damping. So both damper is working simultaneously. Okay.
So this is the other people want to see on the. So we can see the hybrid damper here.
Oh, if this damper is okay or not. This is the only damper we know. This is one idea. But always also we must be careful about patent. If we, for example, ask the Smith Moriko company to produce this plastic damper, maybe we must think about our original metallic damper. This is just one example. Another type is doctoral thesis we read. There's some, I forgot.
The fuse sensor, the still fuse at the end.
Yeah. So the section is like this. They somehow taper the section. So they expect yielding here and connecting viscoelastic damper and another tapering
Here, sensei.
And they expect to yield in here. Yeah, this one. So they have, tapering is here and here. So this is another type of metallic damper or fuse. They call it fuse. Also, we can kind of a hole to cut section. The point is how to dissipate energy at the end of beam. So,
Sensei, I also thinking one point that because we use metallic damper as the fuse, the viscoelastic is only can displace 2 times of the thickness that of the viscoelastic material. For example, our viscoelastic M, and the maximum displacement for the viscoelastic damper only 10 mm. So if the building need more displacement, it can took from the
No. If you, one layer is 5 meter, right?
Yeah.
So you can deform 10 millimeter only.
Yes.
But
only
if you increase the layer, you can deform any. I mean, if you want to deform 50 millimeter, so you put the 5 layer.
Sensei, actually, if we look at the layer, how can I say? Between the one layer of viscoelastic, the plate displays in 2 different directions. So
You are right. Yeah. We can increase force, but we cannot increase deformation.
Displacement.
Okay. Yeah. So
in the Sumitomo Riko catalog also they mentioned that.
Yeah, you are right. Yeah. No, but how to spend? Maybe. So, I don't know. 5 meter viscoelastic and separated by steel plate. So you can say total 15 millimeter thickness might be possible. And なんて言ったらいいかな。For example, in case of 2 layer, one is middle steel, and the other side there will be another. I'm looking from the top. Okay.
Yes, I understand.
The viscoelastic material is between steel plate. Right?
Yes.
So from horizontal direction, so the other side will be like this. And this vertical deformation, D, and this is a thickness, let's say H. And from Sumitomo Riko, maximum deformation is almost 200%. So it will be 2H, right?
Yes.
So if this is thickness is 5 millimeter, this deformation is less than 10.
Yes.
So to increase this deformation, you must adapt very thick viscous material here.
Last meeting sensei with the company, they have 15 and Majima-san asked about the thickness and they said they are now try to run it for 2 centimeter. Yeah. 2 centimeter.
Not 5 millimeter.
5 millimeter is already available, but they want to increase the thickness until 2 centimeter.
Yeah. So what my idea is like this, and another one like this, and like this. But here we can put the 5 millimeter plastic material separating steel plate.
I understand.
So 5, 5, 5. In total, 15 millimeter might be possible. I don't know if it's really available or not.
Maybe we can ask to the company for the next visit, sensei.
Okay, okay. Yeah. Okay, good. So we must discuss more about the capacity spectral method and displacement-based design method.
Right.
Yeah.
Sensei, we can discuss the time available later.
For the meeting, one by one?
Yes, please. Face-to-face meeting.
Face-to-face meeting.
When you available?
Maybe next week. Let's see. So. How about Monday, 11 o'clock?
Monday.
23.
I'm okay, sensei.
11 o'clock, okay?
Okay.
Yeah. Okay. Sarah-san, are you here?
Hi.
Did you submit the document for 実務訓練?
What?
なんだっけな。実務訓練の、なんだっけ。You must submit some document.
Oh, okay.
And you are in the list of students who did not submit it. さっき連絡表かな。10月17日まで。I show, this is a message from Career 支援係. This is your name.
Yes.
And you must submit Excel file about 配属先連絡. This is for the October 16, 1809. Did you receive this email?
Okay, I will check.
Okay, so if you didn't submit this, you cannot, you will not be accepted.
はい、わかりました。
Be careful. サラさんは今日何するものある？
あります。
あります？Okay, so please.
Can you say the okay. it have the two models of the first 600 times 250 and 750 times 300 steel coupling beam, and so the design criteria checking, and this is here. And this is interesting. And this yellow line is a limit, and
Okay.
and all of the
Then satisfy
yes.
the limit. Mhm.
And the first one is, and this one is a wall one that, and blue line. This two blue line is 7.5 meter, and green one is a 5 meter wall. Red one is 2.5 meter wall, and this is wall to ductility, and this is coupling beam ductility. And after that, and this is a metallic DBTM's result. Before meeting, I showed it, but now I wanna show this viscoelastic dampers. 2.5 meters. All designs of them is not good because this target line is over the capacity curve. So I wanna show the 5 meters from the 5 meters. And from
So, Sarah-san, could you go back to the story drift again?
yourself.
Yeah. I mean, could you go back to this one? So, all story drift is less than target.
I
150.
I have question like why the story drift is like less than the limit? Because my story that I show is 10 story. This is 15 story. It should be more than limit.
I don't know. Maybe time period, natural period is longer. So if you increase number of story, 15 story, so natural period is longer. So earthquake effect is not so much. That is
Understand.
why the response is smaller. Maybe.
I will check the exact later sense.
Sorry, I have a phone call.
Okay. Can I
ちょっ
turn?
と待って、ちょっと
Okay.
Sorry, please continue.
Okay.
So actually, you don't need to put damper because already only steel beam satisfy and target. So that's why all the result by displacement best design is over than capacity curve because already building satisfy.
This is 5 meter.
Okay. But anyway.
Okay. Viscoelastic 100%. This is just a little bit over the capacity curve. This target line. And this is a 7.5 meter wall with scholastic 20%. And this is perfectly result. And increase the properties. This is the result after the 40%. And I want to show this under the intro, the 5 meter and the 7.5 meter story tree.
But the story drift you showed before, it is much smaller than this one.
Yes.
Now, why? Why after you put the damper, response is larger? Why? Safira-san, why?
I have one same question, Sensei. That's why I asked her like why the limit is less than yeah. Maybe
I
to
will
check.
try check.
Yeah, I will check her CSM later, Sensei.
Okay.
And this is under the
Okay.
yeah. And summary of the table of the metal damper. Choose the 20% and from the viscoelastic damper, and the best variation of the dampers 7.5 meter walls, 20%, 40%, 60%, and the 5 meter walls 100%. And the next step is check the combination of this one.
Okay, so
100.
please talk with yeah, and to check maybe
The
the
capacity
result again.
spectrum.
Yeah. Capacity spectrum. No. I don't. So anyway, if the building with a damper doesn't satisfy the criteria, then we put the damper to somehow, it's a kind of retrofitting, right? We replace steel beam with a beam with damper to make it better performance. But it looks your building is okay from the beginning. So, and after putting damper, the response is even larger than before. So,
something's wrong there.
something is wrong. It's better to check. Okay.
Yes, sir.
Yeah.
Okay.
So who is the next? Ataya-san, maybe?
Hi, Sensei. Can I share the screen? I modeled this 7-story frame building.
Yeah.
And analyzed under 4 earthquake. Under Kobe, there is damage the building and 2 connection points. And on the left, there's not too much yielding. And I draw the capacity curve. Vertical is shear force, base shear force, and the horizontal is the displacement. If I did idealize this curve to 3 straight line, and the tangent of these angles are the stiffness stiffness 1, stiffness 2, and stiffness 3. And for the values, then I changed this stiffness to period to time. This is 3 periods and these 3 regions that is increased. So I consider 3 time period. This is the natural time period. It's 0, and this are also calculated for these 3 regions. So I applied for TMD first single TMD tuned with this time period, then 2 TMD with this 2 time period, and 3 of them, and 4 TMD with
Oh, okay.
and these are the values of stiff damping, coefficient damping of the dampers for single TMD, 2, 3, and 4 TMDs.
Okay.
So this is the lateral center. The black line is only one single TMD. The blue line is for 3 TMD for and 3 and radius for 4 TMD. It's the percentage reduction percentage. You can see that 4 TMD reduced the displacement very much. The other under Kobe also it is better than other 3 scenarios. Under Taft, 3 TMD is better, and under Tohoku, 4 TMD is better as El Centro and Kobe. And the result under the Taft is because the maximum displacement of top story is about 7.4 centimeter. So we dedicated a TMD which exceed the TMD under Taft. Because of that, maybe.
Okay.
Because the mass we dedicated in this part doesn't work for Taft. So totally, we can say that this methodology work very well, I think. But
Could you tell me how did you calculate displacement reduction percentage? The formula. Why it can be negative?
Because with single TMD increased since the display was it doesn't work because it is tuned with the linear stage of the building, but building goes to the non-linear region. So when we tune that single TMD for that natural period, it doesn't work properly because of that. It has
So reduction percentage is original story drift minus story drift with TMD
yes
divided by original story is
divided again by without TMD displacement with TMD, then by 100.
Yeah, maybe so. It's
For example,
negative if I mean deformation increase, displacement increase after putting TMD. This part is
yes,
negative.
yes.
Yeah.
And for this model, it's that's all. But I'm thinking about something else. In here, since the mass is the total mass of the building, and these values are obtained. But if I use instead of this mass the effective mass ratio, then this T will be very similar to the natural period. And if I use the instead of the total mass, the effective mass ratio of the then this periods will change, and I can apply only 3 TMD. That for this T and natural P, it would be the same. So we don't need to use 2 TMD.
Okay.
Yeah, and the previous research for mid-rise or short-rise buildings like 7-story, don't need use we don't need control the higher modes. Only the first mode is enough. But I want to model a 25-story. This 3 TMD for the first mode, and I want to design 2 other TMDs for the second and third mode also, and see what would be the results.
Okay. Well, that is interesting. Yeah.
And in here in the middle, because there is a problem maybe design, because for the first, second, third, and fourth story we have strong columns, but the dimension and the rebars of the fifth, sixth, and seventh story. Because of that, in the middle, the building is soft, so the displacement is higher. Because of that, this percentage is, the line is like this.
Okay.
Yes, that's all what I want to check the things that I explained, Sensei.
Okay. Any question from students? No question. So, Ataya-san, I must also discuss about your, how to say, job hunting. But
Yes,
maybe we must discuss face to face, right?
okay, Sensei. Yes.
Where now?
I am in the room, Sensei, not in the lab today.
Oh, okay. Could you come to my room after this meeting?
Sorry, Sensei, I registered for a job hunting presentation. It starts from 3 o'clock.
Oh, what did you say? Job hunting presentation?
Yes, there's a seminar by JITRO. There are many can present for new graduates.
Oh, okay, good. Yeah, I'm happy to hear. Please attend meeting. Yeah. I am a little bit worried about your, job afternoon. It's not so easy to find a job in Japan. Yeah. So, yeah.
The language is not good, it's difficult.
OK、クイズ、真島くんさ、元気昨日なかったけど。
はい。すいません、忘れてました。
忘れてた。そっか。
カレンダーに入れてなかったです。
体調悪かったのかなと思ってさ。ちょっと確認した。住友理工の、
はい。
工場見学は一応メンバー入ってんだけど、行く？
その日、クレーンの免許の授業が参加できないです。
じゃあ、真島くんは行かない。
はい。
OK。アハメドさん。
Yes, Sensei. Yes.
Are you interested in visiting Sumitomo Rico company?
Yes, I can
Okay,
go.
okay. So I will be here.
Okay, thank you, Sensei.
So it will be Friday next week. Yeah. Okay, good. 小島くんと相談するのはいいかな。ここでなんか報告することある？真島くん。
はい。
はい。じゃあ、お願いします。
今スライド見えますか？
あ、はい。
6小試験体で、このリニアガイドですけど、リニアガイドのボールと、
うん。
この真ん中にあるボールとレールの接触面で発生する摩擦力の
うん。
モデル化について、カタログでは、リニアガイド
うん。
1セットあたりの摩擦係数が0.003っていうふうに記載されていて、これをどうやってモデル化するかなんです。今は、振り子の免震装置のところの摩擦係数を0.003にして、
バリニアにすればいいんじゃないの？
あれって軸力自分で計算しないといけないってことですよね。
ああ、そうか。そういうことか。そうだな。
変異荷重が分かってるわけじゃないので。
そっかそっか。
それが、まあ、ちょっと、はい。ほぼ直線、リニアガイド直線なんで、もう、これが限界の値だったので、もう半径実機はほぼ直線と考えて一緒になると思ったので、この一番大きい値にして、中心はリニアガイドのブロックの高さにして、限界変異はリニアガイドの最大変異を入れて、あと質量とかは計算、3D モデルの体積から密度をかけて計算しています。これで免震装置がある場合、左がない場合で、右が4箇所に免震装置を置いた場合のモデル化を。
リニアガイドってなって、ダンパーの扱いになってるわけね。どこだ？
リニアガイドは、この I1 のところです。積層ゴム扱いです。
免震は
この D1 に分かれてます。2つ、手前側と奥側に置くために。
でもこれは全部軸力、免震の方に入っちゃうな。
ダンパーじゃなくてですか？
ダンパーには全く軸力入らないよね。
どうすればいいの？
リニアガイドにどれくらい軸力入るかって実はわかんないよね。
はい、わかんない。
ほとんど入らないよね。
はい。ただ、レールが動くので、摩擦は働くんですけど。
だからわかんないんだって。
それで振り子で一旦やってみて、周期自体はそんな変わらないんですよ。1.281と1.274で。で、応答を比べたときが、左が変異応答の図で、右が加速度応答で、青色が積層ゴムがない場合で、オレンジ色の破線が積層ゴムがある場合で、積層ゴムじゃなくてリニアガイドなの。
全然差がよくわかんないんだけど。
ほとんど差はないです。若干最大値が小さくなるぐらいなんですけど、なんか、解析モデルに組み込まないといけないのか、組み込まなくてもいいのか、どうしようって悩んでるんですけど。
組み込まないければ、ちょっと安全側っていうか、応答が大きめで出るっていう感じかな。
そうですね、摩擦がないので。
組み込んでもいいけど、振り子じゃなくて、非常に小さな値を入れたバイリニアの、幸福体力は適当にちっちゃな値を入れる。
初期合成めちゃめちゃ大きくしてってこと？
そう。そうするのかな。
摩擦係数って軸力に比例でいいんですかね？ 0.003 っていうのは。何も書いてなくて、単純に摩擦係数0.003としか書いてない。
これは軸力を掛け算すれば体力が出る。
で、モデル化した方が大きくなるってことですよね。
いや、力がさ、上からの重さが全部リニアガイドに行くかって言ったら、ほとんど真ん中の積層ゴムがね、支えるので、基本的にリニアガイドは重さがかからない方がいいんだよな。
そうですね。
うん。
これ実験結果から計算ってできるんですかね？そのリニアガイドにかかってる荷重。
いや、まあ、ほとんどだから摩擦力ゼロだと思うんじゃない。無視した解析で合うと思う。
うん。わかりました。
うん。むしろこれの結果に影響すると逆に実験の解釈が難しくなるよね。うん。これは難しい。ね。試験体組んでみないとね。応答予測は、まあ、リニアガイドで、
はい。
応答予測すればいいんじゃないかと思う。
はい。わかりました。
はい。
以上です。
はい。Okay, good. So that's all for today. And, Saraya-san, do you have anything?
No, Sensei, I have prepared the presentation. I'll present.
Okay. Yeah.
Yeah.
Next. Okay. So,
And Sensei, I will make the corrections as you have suggested and to Vasant Sensei by today.
yeah. Okay.
And maybe next week we can submit to Soil Dynamics.
I don't know Soil Dynamics is the best journal or not, but anyway, it was quick for review.
Yes, Sensei, and the impact is good for Soil Dynamics. Okay, so.
Okay.
And I will also ask Vasant Sensei if he has any recommendation.
Okay, yeah.
Yeah.
Okay, so next week, Saraya-san's presentation is a Tuesday, 24. And you will leave Japan 30.
Yes, Sensei.
Leave Toyohashi 30.
Yes.
Okay. Maybe we can have a lunch, 25 or 26, maybe.
Okay, Sensei.
Okay. And, so next meeting, when shall we go? どうしようかな。来週は住友理工に、ミーティングは再来週でもいいかな。30周年公演。So,
31大丈夫です。
31st.
I'm okay, 先生。
What time shall we do it? I have a meeting from 1 o'clock, so.
Morning is okay.
How about 10 o'clock in the morning or 5 o'clock, 3 o'clock afternoon?
I'm fine with any time. How about others?
How about 3 o'clock?
Okay, 先生。
Okay. And, everyone attend is okay. Saraya-san, you will not in Japan.
Yes, sir.
Okay. Yeah. Okay. Next control group meeting. 3 o'clock Tuesday. October 31st. Okay. Okay.
先生、I sent the invoice to you. The GAS invoice. I already sent to you.
I didn't
Yes.
receive yet.
Can you refresh?
Refresh. Okay.
Okay.
Also send me invoice and receipt.
Invoice and receipt. Okay. はい。
Okay.
ありがとうございます。
Okay. See you. Bye.
See you.
Bye.